So, as I indicated at the beginning of the last video, one of the main applications of line integrals is when the curve C represents a wire or a spring or a rod or basically some thin material in space. So, for instance, if delta of xyz is the density, this is per unit length of the wire, then the mass of the wire is going to be just the integral of the density now with respect to the curve. So as opposed to integral delta dv over some solid region in space. Note that here, in this case, the units of delta would be like grams per centimeter or like weight per length, whereas here, mass per length, whereas here they would be like grams per cubic centimeter, or so mass per volume. So then we have analogous formulas for all of the concepts of masses and moments we discussed for solids, where now we just replace everything with one of these line integrals. So we just write down all of those formulas for reference. So mass, as I said, is m. It's integral c delta ds. The first moments are m yz, integral c x delta ds. M xz is integral c y delta ds, and m xy is integral c z delta ds. And you could do this with respect to any line, but we mainly care about just the coordinate axes or coordinate planes. With respect to any plane. The center of mass will have, so we calculate from those moments, is m yz over m, m xz over m, and m xy over m. And then the moments of inertia again are, so ix will be integral y squared plus z squared delta ds. Iy is integral x squared plus y squared delta ds, and iz integral, this should be x squared plus z squared delta ds, and this last one will be integral x squared plus y squared delta ds. For these, so the exact same formulas, we just change integral over region dv to integral over c ds. So that's one helpful example to think about like what line integrals mean in general. Another one is, so this will be easier to visualize in the case just of a plane curve, so with no z component. Well, now we can graph z equals f of xy equals f of r of t. So if we've got a curve, let's say our curve r of t is something like this, then maybe our f, by graphing, so I'll do some fancy 3D example to draw this better. In the examples, so we can graph sort of the surface or wall along the curve. So this explicitly will be parameterized by g of t, h of t, and then tau f of gth of t, where t is our parameter for the curve, so it goes between a and b, and then tau is just going to scale the height of the wall, so it'll go between 0 and 1. So then this integral, integral CF ds is the area of that wall.